From our graphs of motion, it is possible to derive a number of equations of motion. Equations of motion can be used to calculate all these different concepts like initial velocity, final velocity, time, and displacement, as well as acceleration. So acceleration is your A value there. What we're going to do is we are going to take a look at how to use these equations of motion. They are all given to you on the information sheet, so you can easily just look them up. You don't need to remember them at all or have some way of knowing which one to use. The way that you know which one to use is based entirely on the question and knowing what these quantities mean. They are all important for rectilinear motion. Rectilinear motion means motion in a straight line. So we are only going to worry about acceleration in a straight line. We're not going to be turning corners or anything like that. And these four equations over here are all for acceleration or an accelerating body. Remember that if you've got a constant velocity, you are going to use VST, which is the triangle that we've been using since you were in primary school, which looks like that. So remember, but that is only when you have got constant or average velocity. If you are working with an acceleration, you need to use one of these equations of motion. So let's see how to use these equations of motion. If a car starts from rest, the first thing we know about this car is that it started. In other words, its starting velocity was 0 meters per second. And it covers a displacement. Displacement is symbolized with an S, and it covers a displacement of 20 meters. And it does that in a time of 3 seconds. The question is, what is the final velocity of that particular car? And that's the first question. And then the second question is, what is the car's acceleration? So we're looking for both of those. Let's first look for the final velocity. If I look at my equations of motion, I see that I've got U, S, T, and I'm looking for V. I do not have an acceleration. So I look at the equations of motion and I see that S is equal to a half U plus V. T includes U, S, and T, and V, but it does not include the acceleration. So I substitute in those values. 20 is equal to a half, 0 plus V, which I'm looking for, multiplied by 3. And when I rearrange that, and this is maths, you really need to be able to rearrange these numbers. Multiply by 2, divide by 3, and then you get your V, and it turns out to be 13,33 meters per second squared. The second one is to work out the car's acceleration. We don't know V. I don't really want to, sorry, that wasn't per meter squared, it's just per meter, per second at least. I don't want to use my potential mistake in that question over there, so I'm going to use the equation of motion. S is equal to U, T, plus a half AT squared. I've got U, I've got S, I've got T, and I'm looking for A. And there's no V in that equation at all. So substituting values, 20 is equal to 0 times 3 plus a half. Acceleration is what I'm looking for, and time squared. And I land up with an answer of 4. A is equal to 4,44 meters per second squared. Again, you need to be able to do your maths here. You're going to say 0 times 3 means that term disappears altogether. Then you multiply the 20 by 2 and divide it by 9. Astronauts are going to the planet Mars, where they determine that the gravitational acceleration on Mars is equal to 4 meters per second squared. Someone leans over the side of the spaceship and drops a stone. Drops, when I say drops a stone, the initial velocity is always 0. Drops mean I gave it no initial velocity at all. Vertically downwards, which means it is underneath, it's going down under gravitational acceleration, which we already know is 4 meters per second squared on Mars. They find it takes a stone exactly 8 seconds to reach the surface of Mars at the foot of the building. Calculate the height of the building. What is height? Height is simply a distance. So distance is what I am, or displacement is what I am looking for. I look through my equations of motion. I've got no final velocity, so I'm going to use S is equal to ut plus a half at squared. And I substitute in my values. I don't know S. I know my initial velocity is 0. I know my time is 8. I know my acceleration is 4. My time again is 8, and I mustn't forget to square it. And when I substitute that all in, I land up with 128 meters. We've now got a cheetah which can reach a maximum speed of 20 meters per second from rest. So what can we write down? My final velocity is 20 meters per second. That's what I end with. I start at rest, 0 meters per second. In a time of 5 seconds, I'm going to work out, they want the acceleration and the displacement. So let's first work on the acceleration. I want an equation of motion that does not have S in it. So I'm going to go V is equal to U plus AT. Final velocity, 20. Initial velocity, 0. Acceleration, I do not know. Time, 5. Rearrange that, and my acceleration comes out to be 4 meters per second squared. Check that you can do that on your calculator. Just because I can do it doesn't mean you can. Now I want an equation of motion that does not include the acceleration, because I don't necessarily want to carry my potential mistake from there to my next problem. So I use S is equal to a half V plus U T, and that is equal to a half. My final velocity was 20, my initial velocity was 0, the time taken is 5, and I land up with 50 meters. We have a taxi driver who is driving his taxi at an initial velocity, that's what's happening to start with, at 40 kilometers per hour. He notices a huge branch in the middle of the road, 300 meters ahead of him. He slams on brakes. It doesn't say he travels 300 meters. It says that he notices a huge branch ahead of him, 300 meters. So let's just put that 300 meters on the side for the moment. We might or might not use it. I'm not sure. We've got a distance. It might not be the one that he travels. He slams on brakes immediately and slows the taxi down at a rate of negative, because he's slowing it down, 5 meters per second squared. We now know that he needs to get to a final velocity of 0. He needs to stop. And we are curious as to what distance would he do that in. And when we've got a distance, we'll compare it to this distance over here and see if he makes it in 300 meters or not. So we firstly need to change that velocity, that initial velocity over here, into meters per second. So let's do that. We need to say 40 kilometers per 1 hour is equal to 40,000 meters per 3,600 seconds. And I land up with 11,11 meters per second. I'm looking for an equation of motion that does not include time anywhere. So the equation of motion is V squared equals U squared plus 2AS. So my final velocity is 0 squared, 0, 0, doesn't matter. 11,11 squared is my initial velocity, to negative 5, because I'm slowing down, and I'll find the distance. When I rearrange that, I see that it takes him 12,34 meters to slow down. Well, that's good news, because 12,34 meters is a much shorter distance than 300 meters, which is how far away the branch was. So he did stop in time. A car slows down to stop at an intersection 500 meters away. So the distance is going to be 500 meters. It's actually going to stop there. The final velocity is going to be 0 meters per second. If the car was initially traveling at, so my initial velocity is 20 kilometers per hour, calculate the acceleration of the car and the time taken for the car to come to a stop. So the first thing I'm going to do is change my 20 kilometers per hour. 20 kilometers per 1 hour is equal to 20,000 meters per 3,600 seconds. So that comes out to be equal to 5,56 meters per second. Now let's substitute in. I'm looking for acceleration. So I want the equation of motion that does not include time. V squared equals u squared plus 2as. 0 squared is equal to 5,56, my starting velocity, squared, plus 2, I don't know the acceleration, and 500 meters. My acceleration turns out to be negative 0,03 meters per second squared. Ideally, I don't want to use that in my next part of the question, so I'm going to use S is equal to a half V plus U T. My distance is 500 meters, a half. My final velocity is 0, my initial velocity is 5,56, and the time is what I'm interested in. I rearrange that, and the time comes to be 179,86 seconds. If I throw a ball up at 20 meters per second, what is the acceleration 1 second after leaving the thrower's hand? You must not forget that when something is on planet Earth, the acceleration at all times in free fall, in other words, when something's not being pushed or anything like that, it's up in the air, is 9,8 meters per second squared downwards at all times.